All right. So I am going to flip around a little bit at the start just to reorient ourselves, because otherwise jumping into linear algebra can feel a bit weird if you haven't been diving into it right beforehand. So what we're looking at, going way back to the top here, is the idea of a set of vectors and whether they are linearly independent or dependent. And again, this is a set of vectors, so imagine three spaces, sort of the smallest space where this gets interesting. So you have three vectors. They can either be three vectors that point somehow in different directions, contrasted with the idea that they all line up in a plane. They still point in different directions, but somehow between the three of them, they don't go in all three dimensions. They only go in 2 dimensions in the 3D world. If you have, so that gives us our pointer, but what do we mean by independent? If I have three vectors that if I take any of them away, I get a smaller span, that's what we mean by independent. That's one interpretation of independent. And another one is, sorry, and contrast that, if we have dependent, then we have three vectors in a plane, put them in a plane. I get the same plane whether I have both vectors that I just kept or all three, I still build the same thing. So by taking one vector away, I don't change the span. So that's one of the interpretations or contrasts between linear dependent and independent. We're going to explore some other ones here. The mathematical trigger for us is this not immediately obvious definition that if we can add our vectors together with multiples, can we add them and get back to the 0 element? In other words, can I follow some of these various vectors and get back to the start? And if the answer is yes, with non-zero coefficients, then that indicates somehow that there's a relationship between the vectors that we can take advantage of and maybe get rid of one. Whereas if we have an example like this, where if I go in this direction with this vector and I go in the other direction up here with this vector, there's no way I can get to the origin with those two building blocks without introducing another vector, or by taking the trivial answer, which is if I take 0 of the first vector, I want to stay where I am, and I take 0 of the second vector, well, okay, I'm still at 0, but that doesn't really count somehow. That's what we're going to define as linearly independent. The only way to get back to 0 with these two vectors here, or a set of vectors, is if I just take 0 of each of them, then that's not very interesting. And that'll be our default case for independent. All right, so going back to page 24-ish. All right. Yeah, we'll do that. So what I was going through at the end of last class was a two-way proof. So proving the relationship between a set of vectors being linearly dependent. So again, there's something duplicated, there's some redundancy in there, to explicitly a redundancy. We showed that if we take a set of vectors that are linearly dependent, so there's some kind of, I can add some of them up and get back to 0 with real multiples of them, then one of them, not necessarily all of them, but at least one of them can be written as a linear combination of all the others. And so I really want to draw a picture of this. So if we're in 3D, if we have three vectors that somehow are all in a plane together, again, it's hard to see this, but I'll draw it as a plane here. Imagine they all live in a plane. Then what we just said in this theorem was, if a set of vectors is linearly dependent, so these ones in a plane are, then one of the vectors can be written as a linear combination of the others. And we can almost see this middle one here. If I took half of this first one and half of this other one, I can get the third vector in the middle there. There's other possibilities in this particular case, but at least one of them can be written as a linear combination of the others. What we're going to show in the next one is the opposite proof. So if I have a set and I know that some third vector, this one here, say, is a linear combination of the other two. So I can build this third vector here in green out of the other two. Then I know for sure that I'm in this linearly dependent world. And that turns out to be fairly easy to show, but the key is building the skill set of writing proofs. How do we actually demonstrate this with some mathematical analysis? So, sorry, I just saw the chat there. If a set is linearly dependent, all you need is at least one non-zero constant. Linear dependent is the crystal case. Everything is zero. As soon as you get anything not that, any single coefficient that's not zero, but it still equals zero on the right-hand side, that will be linearly dependent. We'll actually take advantage of that, I think, in the next slide after this. So stay tuned. All right, prove the redundancy. Right, show that if one element in a set of vectors can be written as a linear combination of the others. So let our set be V1 to VP, be a set of vectors, and VP is equal to alpha 1 V1 plus alpha 2 V2, that's all the way down to the end. Except we don't want to keep the last one in there. So we're going to stop a little bit early. So we'll stop at P minus 1, V, P minus 1. Keep changing my V forms. All right, let's erase that. That is, VP is a linear combination, of the other vectors. So if one element in the set can be written as a linear combination of the others, that's what that translates to mathematically. Show that it is linearly dependent. Well, that means that we need to put it in that form that we need for that test. So that's right in the blah, blah, blah equals the zero vector form. What does that look like here? Well, let's move this over to the other side. So I have the zero vector equals alpha 1 V1 plus alpha 2 V2 plus alpha P minus 1 V P minus 1. And then this term here, of course, turns into negative VP. But I'm going to make it more explicit. I've got negative 1 VPs. Well, this is a non-zero coefficient. This is the zero vector. So I have a linear combination of all my vectors in the set, which add up to zero, which get me back to the origin, and at least one of the coefficients is non-zero. So at least one coefficient is non-zero, and that's all it takes. In fact, all the other ones might have been zero. We don't know, but I know for sure that this one is negative 1, so it's definitely not zero. And non-zero, which implies that the set V1 to VP is linearly dependent. Okay. Sorry, I just saw Darius' comment. A lot of it's just working with these things for a little while. It takes some time. Hopefully low weeks, because your first test is coming up at the end of the month, but actually not the end of the month, the 14th, a couple of weeks. But honestly, it's wrestling with the concepts by doing the practice problems, whether it's the ones in the tutorials or the ones that are in the sections of the textbook, whatever works better for you, or both ideally. But it's trying to imagine what these scenarios are looking like. It's trying to do the calculations like this proof here. It's basically working with it more and more and trying to, if there's any doubt, if there's anything you need to clarify, getting that question out there as soon as possible, talking with colleagues, talking with me or the other instructors and TAs, and getting some answers for it. But the way to tease that out is by looking at the practice problems and saying, what am I struggling with? What am I not struggling with? Yeah. I'll tell you a story, but not for today. But anyway, I've got a crystallization moment that occurred to somebody else. I'll tell you in another lecture. All right. Going back to that non-zero question and one value. If we take a look at some sort of borderline cases. So if I have the set just zero, and if I had the set down here, it's going to be almost the same set. So I want to put these really side by side. So V1, but V1's not zero. If we set up the equation for linear independence, we are looking at the zero vector times an alpha equals the zero vector. And our question is, what values of alpha satisfy this equation. And identically down here, if we do alpha times v1 equals the 0 vector, it's the same question. I'm just going to copy it. So if we have a single vector, there's two cases that fall out of this. The 0 vector equals a 0 vector. What would possibly satisfy this? Well, can I put a 2 in here? Well, sure. 2 times the 0 vectors is a 0 vector. That's actually one of the properties from the axioms of a vector space. So could I put 10 in here? Yeah, absolutely. I can put any non-zero alpha, or yeah, alpha will work. And again, that's a non-zero thing, which means that the set of the 0 vector by itself is linearly dependent. I can get back to the 0 vector by using multiples of the 0 vector. That's kind of trivial, but it satisfies that definition for linear dependence. Whereas contrasting down here, only alpha equals 0 satisfies this equation, because we already said that our vector was not the 0 vector. So if I have a scalar times a non-zero vector equals 0, then the only way to make that happen is to have my alpha be 0. And so any other single element set will be linearly independent, is linearly independent. So again, I wish it was a little more clear that if you have a single vector, it's always linearly independent. Well, that's true as long as it's not that the 0 vector itself in your set. So the question is preferable versus not preferable. It's actually not that. It's more a recognition. When you find a set of vectors is linearly dependent, you're like, oh, that tells me something about that set. In particular, it tells you that there's something redundant possibly in that set. And we're actually going to see this play out at the start of next week, where linearly independent versus dependent just means that there's something else you can infer. It's going to be about linear systems of equations, something else you can immediately infer about the number of solutions. So it's not one's better or one's worse. It just tells you something different about the set. So no judgments, just qualifications, just descriptions. All right. A couple of other boundary cases. If I have a 0 vector with some others, so the last time we just had one single vector, the 0 vector by itself. What if I had the 0 vector in with a bunch of other things? Well, not too surprisingly, we're going to get a linearly dependent set out of this, because we have the 0 vector times alpha naught, let's say, plus v1, whoops, I have to remember my alphas, v1 plus alpha pvp, alpha naught. So this is our standard form where we have each vector included, and then we have each vector is multiplied by some scalar that we get to pick. Here, again, we might have all zeros for the other alphas, but I can pick any non-zero value I like for alpha naught, and 0 for all the others, or all other alphas. But the key thing is we have one non-zero value. That's all it takes. At least one of the coefficients. And the equation is non-zero. That means that our set of the 0 vector and this other bunch, doesn't matter, will be linearly independent, linearly dependent. Okay, so somehow the 0 vector being by itself means I can get back to the 0 vector with multiples of my vectors. But the same thing is true even if I have the 0 vector combined with, say I had the 0 vector and 3 vectors that are nice and separated in 3-dimensional space. Because the 0 vector is in there as well, it's still a linearly dependent set. I can use multiples of that to get the 0 vector and just cancel all the rest of them out. So this is the best example of all it takes to be linearly dependent for a set is that even one of these coefficients is non-zero. All right. The alpha naught associated with vi. The alpha naught is associated with the 0 vector. All the other v's, because we started counting at v1, I used alpha 1, alpha 2, and so on, but I just made that should be a sub-0 to make it a little more clear there for reading. So I just pick 10 of these plus 0 all the rest of them. That's guaranteed to add up to 0, and that is a solution with non-zero values in it. Exactly. So if the 0 element is in any set, whether it's by itself or with a bunch of others, you have a linearly dependent set, guaranteed. That's a nice, doesn't happen often again, but if it does come up, it's like, oh, I can tell you immediately what category this set of vectors falls into, dependent or independent. Okay. Now, what about collections of sets and adding and subtracting from them? So often we'll get a bunch of vectors, and then we're like, well, what if you take one of those away? What can we say about that? Or we have a set of vectors, and what if I add one with certain characteristics? So here we're given, so whenever it says suppose, this is something that's given to you. You're starting with the assumption that I have 4 perfectly good vectors that are linearly independent. Okay, so I can't visualize this because in 3D, because you can't get that many linearly independent vectors in 3D, but the math is clear. That statement means that the equation alpha 1 v1 alpha 2 v2 plus alpha 3 v3 plus alpha 4 v4 equals 0, the 0 vector. That equation has only one solution, which is alpha 1 equals alpha 2 equals alpha 3 equals alpha 4 equals 0. So that's our correspondence between the words up here. Hey, a set's linearly independent. Okay, well, what's the test? The test is that when I add up a linear combination of those things and have it add up to 0, the only way to make that happen is to have all 4 coefficients 0. So that's our starting point. Well, what if I then have those 4 vectors and I say, well, what happens if I shrink the set a little bit? Can I say something about the relationship between the 3 that are left? So I'm going to throw out, for no particular reason, v4 at the end there. Can I then say that the smaller set is linearly independent, dependent? What happens when we do that? Well, just intuitively, let's go down to 3D again. So it's, again, the nice space. So if you start with 3 linearly independent vectors, if you take one away, you do get a smaller space for the span and all that. Like I had 3 dimensions I could cover with these 3 vectors. Now I can only cover 2. But the relationship between those 2 vectors is that they're still linearly independent. They didn't all of a sudden become, parallel to each other or something else. So if I have the multiple vectors that are independent and I take one away, it feels like that new set is likely to be linearly independent as well. And the answer to that is actually that's true in general, and we can prove that mathematically here. So we now consider the v1 alpha 1, let's call it beta 1, because it could be a different coefficient. Beta 1 plus beta 2 v2 plus beta 3 v3 equals 0 equation. All right. What we're looking for is whether there might be non-zero values that solve this equation, but that didn't satisfy the other one. So this is going to be what is called a proof by contradiction. We're going to end up getting to a point where if I assume what I'm going to assume right now, it leads to something that I know is not true. So proof by contradiction here. The way we structure this is assume there, so this is the fancy backwards E here, and that just means there exists. There exists. Beta 1, beta 2, beta 3, at least one non-zero, at least one not equal to 0, such that beta 1 v1 plus beta 2 v2 plus beta 3 v3 equals the 0 vector. So remember, this is basically saying, I think this set is linearly dependent. So we're going to assume that it's linearly dependent. And then we're going to see, well, if that's true, if that's okay, maybe that's true. But if I do that, then I'm going to get a contradiction with what I said earlier. And that means, well, then this can't be true. So we can work our way back and say what I assumed at the beginning has to be untrue. But then beta 1 V1 plus beta 2 V2 plus beta 3 V3. And now I'm going to add something here. I'm going to add 0 V4s equals 0 vector. Why am I adding that? Well, because there it is up there. The equation that I know something about for sure is this equation up here. So if I add 0 V4, it doesn't change anything to the value. We know adding the 0 vector doesn't change the vector quantities. And so we have this equation here equals 0 also has beta 1, beta 2, beta 3 not equal to 0 for some, at least one. At least one of those, as I said before. But think about what that tells us about this four vector set. One of these values is non-zero. It doesn't matter that this is. At least one of the values in any of the coefficients is non-zero, and I get a 0 vector in the end. That would mean that the set V1 to V4 is linearly dependent. Did I remove space for this? I did not. All right. I'm going to add a little page here. Hopefully you can write smaller than I can. There we go. And then I'll just slide this a little bit. So this is saying, hey, if the smaller set is linearly dependent, then that means the bigger set also has to be linearly dependent. But our assumption was, but we know, probably better, we know V1 to V4 is linearly independent, which means that our assumption was wrong. Our assumption, which assumption? This assumption here. This assumption here is wrong. It must be wrong. And if our assumption is wrong, our assumption was that we had a linearly dependent smaller set. The only way to be wrong from that is to be the other kind of set, which is linearly independent, which means V1 to V3 must also be linearly independent. All right. So this is saying if we have a big set of independent and we take one out, take one vector out, and we get a smaller set, then it'll also be linearly independent. That's what we can prove with all of this machination here. Yep, if we know we have a known linearly independent set here, then we can remove an element of it, and whatever's left is smaller, but it's still linearly independent. The relationship between the vectors still has that linear independence to it. And then I could repeat that. So I could go down to one vector and still keep it linearly independent. And away we go. All right. Sorry, I should add one thing at the end here. Down to the empty set. We show that the empty set is not linearly. Anyway, the empty set's not really one of interest. I'll just leave it at that. Okay. So let's take a look at this contrary version where we have a smaller set of vectors. So we're starting with V1 through V4. Is it not good? Yeah, you've got to be careful. Sorry, I'm just seeing the chats there. You have to be careful about which set you're specifically talking about. Are you talking about the one with all four? That was given to us as being linearly independent. Or where there's a 3 set that we kind of played with and said, well, I don't know. So maybe it is, maybe it isn't. What if it isn't linearly independent? What if it's linearly dependent? What would be the consequences of that? Oh, that consequence I don't like. That consequence doesn't make sense. So I go back and I change my mind and say, no, those first 3 have to be linearly independent as well. So the big set is, Then we tried, what if the smaller set is not? And realized that leads to bad places. So we said, oh, then the smaller set must also be linearly independent. This one I think is nice graphically, or at least intuitively, again in 3D. So we have a small set, and we're told that V5 is in the span of, which should be a red flag for things we've seen before, because we actually covered this kind of example in our redundancy thing. In fact, we could just go back a few pages, but we'll do this one mathematically with the context of this example just to show it. That means that V5 is equal to alpha V1, alpha 1 V1, alpha 2 V2, plus alpha 3 V3, plus alpha 4 V4 for some alphas. And notice we don't actually have to have these be non-zero. This is just, we said that V5 is a linear combination of, can be written as a set of the sums and scalings of the first four vectors. And we actually did this before in the general case, but we can do it here in the specific case. We're going to take this V5, put it to the outside, and that means we have the zero vector left on the left. We have alpha 1 V1, alpha 2 V2, alpha 3 V3, and alpha 4 V4, minus 1 V5.
Excuse me.
Sorry, go ahead. Yes.
Could you just very quickly just redefine what span is? I know it was said in the earlier lecture. I don't really remember right now.
Yeah,
Just
so it literally means it can be made as a linear combination of those vectors.
Okay, so so instead of the linear combination equaling 0, it equals that vector?
Yes. So the intuitive sort of graphical way to interpret span is, can I reach V5 using these four vectors as the building blocks? And adding them or scaling them.
Okay.
Yeah. So
okay.
We're allowed. Does that make sense?
Yeah, it does.
Okay. No, I'm glad you asked, because I'm sure there are other people going, wait, span, I think I vaguely know. So span is, I have some building blocks. I'm allowed to stretch them. I'm allowed to flip them. I'm allowed to add them to other stretched and scale versions of the other vectors. So it's any linear combination is what I'm allowed to do. Can I get it to add up to V5? And here we're being told, yes, you can make V5 out of these ones here. And then the linear independence question is about the zero vector. So is the set V1 through V5 here linearly independent or dependent? Well, hopefully you're flashing to dependent right now, because there's this equation that equals the zero vector. I should copy it. Let's do this correctly, because alpha 1 V1, I'll just expand it out here, to alpha 4 V4 minus 1 V5 equals 0 has a solution with at least one non-zero coefficient. I don't know what the alphas are. I don't care, but at least one of these numbers here is a non-zero coefficient. And that means the set V1 through V5 is linearly dependent. All right. Yeah, sorry, I shorten linearly here all the time because life's too short. LIN apostrophe LI is linearly. So just to reinforce, you didn't necessarily have to do this, because we actually had a proof a few slides ago, and I'm just going to go back to it right now, that covered this in the very general case, this one here. Show that if one element of a set of vectors can be written as a linear combination of the others. So for us, we have a set of vectors V1 to V5. One of them can be written, so they said V5 could be written as some combination of the others. Linear combination, that's what the span meant. V5 is in the span of the other ones. And so as soon as we know that V5 can be written as some combination of V1 to V4, we know immediately that the whole set together will be linearly dependent. So that is just an example of a specific case, whereas this was actually covered in the general case. So you could have just quoted from the earlier result about linear dependence when one of the vectors is in the span of or is a linear combination of the others. All right, where are we here? Okay, now I do want to change gears here, just because we haven't messed with the strange, weird vector space in a while. This W2 looks like R2, except it's only in the upper right quadrant. So it's only in X and Y's that are greater than 0, not even on the axes. And what makes this work, it's kind of like a log exponential thing. When we add, in this new world, when we add two vectors, what we do to the coefficients is we multiply them as real numbers. So I take my first coefficient, second coefficient, and multiply them. Then I take my, first coefficient, and then second coefficient, and I multiply those. So this is a flashback to about 2 weeks ago. If it's not top of your mind, that's totally reasonable. But we can look down here, and this is included in the slides for your reference. Also, kind of like addition now looks like multiplication to us normal mortals. Multiplication turns into exponentiation, kind of the same hierarchy. So if I take a scalar times a vector xy, what I'm actually going to do with that in this space is do the x to the power of that alpha and y to the power of that alpha. And what that does is it changes a whole bunch of things and certainly blows your intuition out of the water, which is sometimes healthy. So here we've been given two vectors, and we're asked, are they linearly independent or linearly dependent? Same thing. And here we really have to go back to the definition. If you're ever confronted with a new scenario, if this is two vectors from regular R2, you say, are they parallel? Well, they're not parallel, so they're independent. No, they're parallel, that's dependent. No, you don't know, because we've changed some rules to go right back to the ground. What we're asking is, does alpha 1 v1 plus alpha 2 v2 equals the 0 vector does this have a non-zero alpha 1, alpha 1, or alpha 2 solution? Right. So in terms of the midterm, I will talk about that at the end if you like. We have the best way to answer that question is to have you look at all the midterms. And so I'll show you where those are on cue at the end of the session today. Or whatever time. Perfect. So yes, we'll definitely address the midterm question as it is coming up. All right. So does this have a non-zero solution, yes or no? Because that's really what defines linear independence or not. To be able to do that, what we really need to do is define our vector now. Well, we have to be able to work with it. So we have to be able to work with it at the level of the operations that we know, which is component by component. And so we're going to define, x1, y1, and v2 will be x2, y2. I'll keep the alpha 1s. So all I'm doing is defining this vector as actually two components that I can work with, two components here. And this, here's a pop quiz. Does anyone remember what the 0 vector is in this space? Yes, sorry. That's all you remember. Vector spaces, that's all we need, is addition of two vectors and multiplication of a single vector by a single real scalar. Yeah, 1, 1, fantastic, excellent. Because if you, again, I'm going to put air quotes around all these things. When you add 1, 1 to any vector, it's like multiplying by 1, multiplying by 1. That doesn't change anything. So that's what, if I add by the 0 vector, the 0 element in this set, the 0 element has to be the element 1, 1. All right. So if that's the case, then let's put in, I actually have numbers here. So let's put in our real numbers, 2, 3, and 4, 9. So alpha 1, 2, 3 plus alpha 2, 4, 9 equals 1, 1. So this is our specific v1, v2. And then what we're going to do is actually use this multiplication operator. So if I have some number times x, I do x to that power, or x is 2 here. So we're going to have 2 to the power of alpha 1 and 3 to the power of alpha 1 plus exactly the same thing here. Where does this alpha 2 go when I bring it in? This alpha goes into the exponent. So I'm going to have 4 to the alpha 2 and 9 to the alpha 2. Make that look different. Equals 1, 1. And then last but not least, we need to do this plus thing, which means take the product of the first components and the product of the second components. So 2 to the alpha 1 times, that's what our addition here in air quotes means, times 4 to the alpha 2 and 3 alpha 1 multiplied by, as a real number, 9 to the alpha 2 equals 1, 1. And our question is, going back to the linear independence test, is there a non-zero solution? Can I find alpha 1 and alpha 2s that work with this? Well, now that we're down to components, we can actually look at each component like we've done in some other examples. We have 2 to the alpha 1, 4 to the alpha 2 equals 1. And you can imagine some scenarios for this, right? Like if I have 2 squared, that'll equal times 4 to the minus 1. That'll give me 4 times 1 over 4. That'll cancel out. So you can either try examples or you can kind of reason with it. Let's do it this. Yeah, I'm trying to think what's some people are more comfortable with exponents than others, and I don't want to freak people out. I'm just going to do the trying, guessing, and checking here. So I'm going to try alpha 1 equals 2. So 2 to the 2 equals 4. And alpha 2 equals minus 1. So 4 to the minus 1 is 1/4. So if I do that, I get a quarter, and I get a 4, and I'm multiplying that equals 1. So that actually works fine. What about the other component? Well, the other component, it has to work as well. But if I do 3 to the alpha 1, 9 to the alpha 2, that's going to be 3 to the 2. Oh, wait, this is exactly the same pattern. Times 9 to the minus 1 for my other one. That's 9 times 1/9. That's equal to 1, 2. So that's fine too. So alpha 1 equals 2. Alpha 2 equals minus 1 is a non-zero solution. We can find a non-zero solution. Solution. Come on. Solution, which means that in W2, not in regular, not in our typical real dimension 2 space with normal plus and scalar multipliers, but in this space here where plus means this new thing, then in W2, those two vectors, 2, 3, and 4, 9, that set is linearly, think about it for yourself in your head for a second, independent, dependent, dependent. They are in some sense parallel. And if you take a look at them and you think about what the operation is, multiplication is kind of how we add or we do powers. Like 2 squared is 4, 3 squared is 9. So this actually is, if you like, this times the number 2 is equal to this vector here, where times means what we have in this scenario. So that, I don't expect everyone, some people I'm hoping are like, yeah, that's fine, it's weird, but if it makes you happy, fine. But if it's not clear, then just go back step by step through this calculation and go, what are we actually doing at each step? We're just using the rules of this world. It's like a new game. Each game has its own rules. We're just using the rules for this game because we were told we're working in that space. All right, there's some questions going by. In a question like this, would be given the operators, we have to, we cannot lie to you. We cannot frame this question without being super specific. By default, if we say the reals is the usual. Sorry.
Sorry to cut you off.
Okay, thanks. If we say the reals, if we say functions, and we don't say anything else, it's the defaults. You'll see this in the old midterms, and that'll make it a little more clear. It is hammered. It is right there. It is in your face. By the way, we're not using the regular ones. We're using this for addition. We're using this for scalar multiplication. So we will never hide that from you. If we want you to use new rules, it'll be super obvious. I cannot harp on that because I don't want anyone walking away going, well, I know. You will know. It'll be like a paragraph at the top of the question. All right. Why do we redefine these things? Because you actually have done it all the time. Between reals to vectors, we had to redefine what vector addition meant, and we did something intuitive or reasonable with it, but it wasn't obvious. Like Descartes had to come along after 500 years of algebraic work and go, hey, you know what? If we package this x comma y, that's really cool. We can do some stuff with that. Same thing with functions. You are actually doing it differently because of the way we write math. It just isn't as apparently shocking as it should be otherwise. We've kind of honed off some of those rough edges. So when you walk into this, you're like, oh, it's obvious what we should do. But it really isn't. We're taking advantage of some things that we just kind of take on faith up to this point. Linear algebra and more advanced math in general is about peeling back some of those layers and going, is that really what you think it is? And sometimes we have to recognize that we could define other definitions for these things, and sometimes that's helpful. You'll see that a lot, especially in physics. Anyway, yes, so the 0 times a scalar vector, absolutely, this 1, 1. If you do 0 times xy, you get x to the 0. What's x to the 0? It's just reals, it's 1. Y to the 0, it's just 1. So yeah, that's again one of those nice things that when we've proven a result like 0 real times any vector equals the 0 vector, that applies here, even though we've done something funky with the definition of the spaces. All right, I'm conscious of the time. I'm happy to take questions afterwards. I know it's a Friday afternoon, yay. But just in the interest of that, I do want to cover at least one kind of example of this type before we wrap up. Functions. So again, this idea of linear independence and dependence is really easy to visualize in 3D, that kind of thing. But it also applies, and I'd say more important for mathematical engineering than vectors in 3 space. I mean, that's great, but functions and their linear independence turns out to be more important for differential equations, for signal processing, for solutions like Rangian approaches to physics. Anyway, yeah, linear independent or dependent functions. So we would consider the equation alpha 1 times f1 plus alpha 2 times f2 equals the 0 element, right? Same equation for linear independence. Or we might call this f1 of x plus alpha 2 f2 of x equals 0. And the way we go from here to here is for all x's in the reals. When we say multiplying functions by a scalar, well, we're doing it for every single x value. And so what we need to have is that these two functions, i.e., these two functions added and scaled, equal the 0 constant function. So that's the paradigm that we talked about with vectors, is I can follow the vectors or scalar multiples of them, add them together and get back to 0. Here, I can add these two functions and always get the 0 function back. Now, again, we can always do that trivially. If I just make the two alphas 0, well, then I just get 0 equals 0. So that's always in the solution set, and that's our linear independence. That's the only answer, but we're looking for other ones. All right. So this turns out to be a little complicated. If they are linear dependent, but straightforward. If for independent sets. So I'm just going to lay that out there, independent sets. What we're going to do for this is pick some particular x values. And this is like one of those annoying things. Hey, I've got an infinite number of solutions, pick one. We always pick some nice number. And students go, well, how'd you pick that number? And like, it'll look nice. That, like, there's nothing more to it than that. It's the same thing here. If this equation holds true for all x's, then it has to hold true for any individual x I pick. So I'm going to do this, and you'll see how the math works out. E.g., pick x equals 0. Then alpha 1, and I'm going to bring in my functions here. So f1 is sine of x. So sine And the x value I'm going to put in here is 0 plus alpha 2 times cos of, well, sorry, f2 is cos. So cos of 0 equals 0. So in other words, I hesitate to draw. I don't think drawings actually help that much in this case. But the question is, if I can take sine of x, then I can take cos of x and scale them and add them up and get the 0 function, then specifically I should be able to do that and have it equal the 0 function at my specific value here at x equals 0. It has to be able to do this for all x's. I'm going to pick 0 for this. Well, what does that tell me about my alpha values? Well, of my alpha values, it doesn't tell me much about this one because sine of 0 is 0. So this whole term goes away. But cos of 0 is 1. And so I get alpha 2 has to equal 0. Oh, that's handy. So to be able to have this equation satisfied here at all x's, I tested x equals 0. To have it work at x equals 0, I need to have at least alpha 2 equals 0. That's a consequence of this first statement. Now, we're in here, yes. What I'm going to do again is pick some other x's. Gosh, what would be a convenient x to pick for sine cos? I think half of you are ahead of me. Hey, let's pick pi over 2. Why? Because look at what was so nice about this. When I plugged in 0, the same thing is going to be nice when we put in pi over 2. Oops, that was really weird, unexpected. What's that? So sine pi over 2. I'll emphasize, it doesn't matter what you pick. You could have picked 1 and 2, 5 and z, not z, 5 and 10. What you would get is equations in alpha 1 and alpha 2. It would work out the same way. It's just more convenient if you pick nice ones like 0 and pi over 2, which you know work nicely with sine and cosine. All right, so pick pi over 2, then whatever alpha I pick has to also equal 0 at this location. Okay, well, what do I know about cos of pi over 2? It's 0, so this whole term goes away. And sine of pi over 2 is 1. So we need alpha 1 equal to 0 as well. All right. Just debating how much to write and how much to say here. Let me walk you through it verbally in the interest of time. What we said here is I'm trying to find a linear combination of sine and cosine that equals 0 all the time. Equals 0 everywhere, every real value. Looking at all real values all at the same time is hard. There's a lot of them. So why don't we say, well, I'll make my job a little bit easier. I'll look at x equals 0. So I go across my axis and make x equals 0 and say, what would it take to make these two things add up to 0 then? Well, the sine function is already 0 there, so I can kind of leave it out. But the cos function has a 1. So if I want to get rid of that 1, I have to pick alpha 2 to be 0. So I kind of have to squish the cosine function down to achieve that goal that I want of a 0 value everywhere. Well, then you realize pretty quickly, well, then if I look a little further along at pi over 2, well, the only way to get my sine function and my cosine function to squish down to 0 with a multiple is to have the sine function also squish down to 0 all the time too. And so the only solution to alpha 1 sine of x plus alpha 2 cos of x equals 0 for all x's, let's say here, for x equals 0 and pi over 2 is alpha 1 and alpha 2 both equaling 0. That's really what we showed, right? So what does that mean for the whole thing? Well, this is a subset of all the reals. If the only way to get it, our sum to equal 0 at those 2 points is to have both of my coefficients be zeros, then that's going to be true. There's no way to have it break out for any other values. I'll let you simmer on that one. That one takes a little bit of thinking, I think. But the upshot is the set of functions, sine x and cos x, is linearly, I added them up, tried to get 0. The only way I could make 0 was if I multiply them both by 0 and wipe them out with my coefficients, that's independent. Somehow they are fundamentally different functions in the kind of world we're talking about. And again, that sort of fits our intuition. We never swap sines and cosines. Now, we are a little short on time to do that one. So I'm just going to introduce another one that is going to be more obviously linearly dependent. So an example, without going through the calculations, of linearly dependent functions would be, let's do something like this. Let's do 1 x squared and 3 plus 2x squared. Okay. In fact, we can use some of the logic we used earlier. If I take, this is called F1, if I take this called F2, and this called F3, if I can write one of them as a linear combination of the others, well, F3, as it turns out, is equal to 3 plus 2x squareds. It's equal to some combination of the other two. Well, if I take, I need 3, if I take 3 of these, alpha 1, F1, and if I add 2 of the other ones, and this is an obvious case because the coefficients are really easy to see, but this is the principle, alpha 2, F2, this is how you would usually show that it's a linearly dependent set, is if one of them is a linear combination of the others. So F3 is a linear combination of F1, F2. Another way of saying that is F3 is in the span of F1, F2. And so there's something redundant about F3. If I have F1, F2, I can build F3. So if I gather all of them together, F1, F2, F3, all together, that will be a linearly dependent set. All right. Now, out of the corner of my eye, I've been seeing the chat going like crazy. So I'm going to stop there for the recording, but then I'll flip over to the chat and happy to stick around as long as people need to wrestle with these concepts. Oh, wait, before I do that, though, I do want to talk about the midterm test, the midterm. So let me just go back to here. 11, why did that not work? There we go. So there will be an announcement about this, I think, tomorrow morning, going out, the usual thing. But if you go to, you will see all the stuff as well. Midterm 1 under test and exam information. I'll zoom this out for you here. So as always, the description of the key ingredients are in the syllabus. The midterm is Monday, February 14th, so 10 days from now. And the core material is weeks 1 to 4. Just because there's a little bit of bleed over into the tutorial 5. We have some questions that are related to that material, and also web work week 5. Some of the material is also covered there. Just so you're not thinking, is it, isn't it? We're trying to be as explicit as we can. It still comes from week 1 to 4. Weeks 1 to 4 content, lectures, and sections from the textbook. That's what's on the midterm. And specifically getting to the questions and the totally reasonable ones about, is this like the question we see on an exam? I don't know what your take on it is, but if you look at the old exams, then you'll know. So typical thing, same as 171 last term, solutions and blank versions. Try the blank versions first, because that's the best test for what you know and what you don't know, and then check your answers with the solutions. All right, that's where I'm going to stop the recording. And now I'll flip back to the chat and answer any questions.